Alright, so in this video we're going to talk about resonance, formal charge, and then also how bond length is impacted by double and triple bonds. So first of all, resonance is when you have a Lewis structure that has more than one possible Lewis structure, essentially. So sometimes you can draw out a Lewis structure and you think there are actually other possible Lewis structures. So let's look at an example. Let's look at carbonate, which is CO3 with -2 charge. All right, so when I look at this, let's go ahead and figure out how many electrons we have. So we're going to draw the Lewis structure. So carbon has 4 electrons, oxygen has 6 times 3, so that would be 18, plus the 2 for the -2 charge. So it's going to be 24 electrons. All right, so that means that's for the available, and for needed, well, carbon wants to have 8, so does oxygen, so that's going to be 8 times 3 would be 24. So that's going to be 32. All right, so 32 minus 24 would give me 8. So that should be 4 bonds. So that means I'm going to have a double bond in there somewhere. So carbon will go in the center. Oxygen, 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 make single bonds between all of them. Well, I know that I'm going to have 4 bonds. So that means that with one of these oxygen atoms, I should have a double bond. Okay, so let's go ahead and finish, and then I'm going to go over the resonance part of it. So I've got 24 electrons, so let's give electrons to the oxygen atoms. So 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Okay, so that is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I have 24 electrons here. That's all of my available electrons. So all of my oxygens are satisfied, and so is carbon. So this is one possible Lewis structure. Well, the fact of it is that that double bond could actually be here or here. So my other possible Lewis structures could be this. Okay, so this is one possible Lewis structure, and then the other one is this. All right, so I have 3 possible Lewis structures here. So the double bond could be here, here, or here, and that's one of the ways that we can demonstrate resonance. So what actually ends up happening though with this is that those electrons are actually, they could be here, they could be here, they could be here, and they're actually moving around the molecule. But we're going to go over that in a little bit. So resonance is when you have more than one possible Lewis structure. So anytime a question is asking for all possible structures, think about where else the electrons could be going.
Ms. Benson, please call extension 1001. Ms. Benson, please call extension 1001.
All right, so formal charge is something that's used in 2 different ways. It's used to show where charges can lie in a molecule, and then it's also used to help select the most probable Lewis structure. So if you can have more than one Lewis structure, formal charge can help you pick the best one. All right, so when you calculate formal charge, what you do is you take the number of valence electrons in the atom. So if it's carbon that we're looking at, then carbon would have 4 valence electrons. And then you're going to subtract the number of non-bonding electrons. So you're going to look at the lone electrons, and then you're going to add that to the number of bonds around the atom. So you're going to look at the number of non-bonding electrons, so how many electrons you have, and not just pairs. You're going to count the actual number of electrons. And I'm going to show you this in just a minute. All right, so let's look at carbonate, and we're going to calculate the formal charge on that. So I'm just going to pick one of them, one of the structures, and then we're going to calculate the formal charge of all of the atoms in the molecule. Oh, it's too many electrons. Okay, so here we go. So we're going to calculate the formal charge of each atom in the molecule. So right now I'm just showing you how to do it, and then I'm going to show you what you do with the formal charge. Okay, so oxygen. Let's look at this oxygen right here. Okay, so the first thing we do is we figure out how many valence electrons that oxygen normally has. Well, it's in group 6, so it has 6. Okay, so 6 minus the number of electrons, non-bonding electrons, so lone electrons around it. And that's not pairs, it's going to be the individual electrons. So 1, 2, 3, 4, 5, 6. And then you're going to add that to the number of bonds you have. So you have one bond here. So it's going to be 6 plus 7, or 6 plus 1 is 7. So 6 minus 7 would give me a negative 1. So I have a negative 1 right here. All right, if I look at this, this would be the same thing. I've got 6 valence electrons for oxygen normally. It's got 1, 2, 3, 4, 5, 6 lone electrons plus the 1 bond. So that, again, that would be a negative 1. All right, so now let's look at this oxygen. All right, so this oxygen would be 6 minus 1, 2, 3, 4 plus the number of bonds, 1, 2. So that would be 0. So the formal charge here would be 0. All right, so I have 0 formal charge here, a negative 1, a negative 1, and then carbon would be 4 valence electrons minus the number of lone electrons, which is 0, plus the number of bonds, 1, 2, 3, 4, which would be 0. So 4 minus 4 would be 0. So I have a 0 formal charge here, I have a negative 1, and then overall my charge is negative 2. All right, so with formal charge, when you look at it, all of the atoms' formal charges, the individual formal charges, should add up to the charge of the molecule. In this case, it's negative 2. So negative 1 plus 0 plus 0 would give me negative 2. If it added up to something different besides negative 2, it would not be a probable Lewis structure. It has to add up to the charge of the molecule. Also, it's really good when the formal charges are as low as they can possibly get. In this case, this is as low as it possibly can get. I've got 2 zeros and I've got a negative 1 and a negative 1. It has to be negative 2. So this is as low as we can get. Also, you want to have the negative formal charges on the more electronegative atoms. Well, that's oxygen versus carbon, so oxygen would be more electronegative. It should have the negative charge. So that's also good. And then when I look, the central atom, it's good to have a charge of 0. Will not always happen, but it's more probable, the Lewis structure is more probable if the central atom is 0. All right, so let's look at another molecule. Let's look at carbon dioxide. All right, so carbon dioxide has, let's see, for the electrons available is 4 in the carbon, plus the 6 in each oxygen, so that's 12. So that's 16 electrons. Now for needed, well, I have 8 plus the 8 in each oxygen. All right, so 24 minus 16 would give me 8. So that means I'm going to have 4 bonds. All right, so with carbon dioxide, I know that carbon should go in the center, oxygen around it. All right, so now I know that I'm going to make single bonds with each of the oxygens, but I know I need 4 bonds. So I can do a double bond on both of them, which would give me this Lewis structure. But I have another option. I could do a triple bond on one of the oxygens. Or it could be on this oxygen. Okay, so now when we look at this, we're going to calculate the formal charges of each of the atoms and then see which one is the more probable Lewis structure. All right, so for carbon right here, carbon has 4 valence electrons. Okay, now we're going to subtract the number of lone electrons, which is 0, plus the number of bonds, which is 4. So it's 0. Okay, so now we look at oxygen. Oxygen is going to be, let's do this one. Oxygen is 6 valence electrons. It has 6 electrons minus the number of lone electrons, so 1, 2, 3, 4, plus the number of bonds, 1, 2. So that would be equal to 0 as well. Okay, so then that means that this one would also be 0 because it's the same exact atom over here. I mean, it's got 4 lone electrons and 2 bonds. So everything here is a 0. So that looks really good. All right, so now let's do this one. Well, oxygen has 6 valence electrons. We're going to subtract the number of lone electrons, so 1, 2, 3, 4, 5, 6, plus the number of bonds, which is 1. So that's going to be 6 minus 7, negative 1. All right, so now carbon, it's 4 valence electrons minus the number of lone electrons plus the number of bonds, so it's 0. All right, so now we're going to do the last oxygen right here. All right, so oxygen has 6 valence electrons minus the 2 lone, 1, 2, plus the 3 bonds. That would give me 6 minus 5, which would be plus 1. All right, so if I look at this molecule, it's pretty much the same thing. I've got a plus 1 on the one with the triple bond, a 0 in the middle, and then a negative 1 right here. All right, so now if I were having to choose the most probable Lewis structure, the one that's most probable is going to have the lowest set of formal charges. So 0, 0, and 0 would be the lowest set. This means this is the most probable Lewis structure. So this is possible. These structures are both possible, but they're not probable because of the fact that there is an option which has lower formal charges. All right, so that's one way that formal charge is used. So it can be used in a situation where you've got more than one option for Lewis structures to pick the best one, or it can also be used just to show where the charges might be distributed among the atoms of a molecule. All right, so the thing about formal charge is that if you get a Lewis structure in which all the octets are met, it uses all the valence electrons, don't look for alternatives with formal charge unless something's actually stated about formal charges. So it's kind of like that saying that says, don't go looking for zebras when you hear hoofbeats. Okay? If you're given a structure that makes sense with octet rule and it uses all the valence electrons, that's probably what it is. Don't use formal charge unless it says something about formal charge or it looks like it could be a funny molecule, basically. When in doubt, just go with octet rule. All right, so now, bond length can change when you have a double and a triple bond. So normally when you have a CO bond, let's say that we have this, it's a certain length. Well, if you have a double bond between the same two atoms, the length will actually change. And same thing if I have a triple bond. So what actually happens is that a single bond is longer than a double bond, and a double bond is longer than a triple bond. So the more bonds I put, the shorter it gets, and also because of that, you have a stronger bond. So this is weaker than the double bond, which is weaker than the triple bond. All right, so let's compare the bond length of carbon monoxide, carbon dioxide, and carbonate. So in carbon monoxide, you're going to get a structure that looks like this. And let me just make sure I have all the electrons here. I've got 4 plus a 6 in here. So it's going to be, oh, okay. So this is going to be my Lewis structure for carbon monoxide. Carbon dioxide should be this. And then carbonate should be this. Okay, so when I'm looking at these, I'm going to compare the length. Well, I can only compare length here because I've got carbon-oxygen bonds. All right, so I know that the shortest bond will be the triple bond. So CO will have the shortest bond. But then I have this here. I've got a double bond here, and then I've also got a double bond here. Well, here's one thing about this molecule right here. I said earlier that these electrons can actually move here or here. Well, if you actually were to analyze this, because of the fact that it could easily be here or here, the electrons are actually moving around among the molecule. So they go over here, and they can go over here. Because of that, the bond length is not actually different between these two atoms and these two atoms. They're all the same length because the electrons can move around. Well, because they're moving around and they're all the same length, that means that the length between these atoms is going to be between a single bond and a double bond. Okay, so that means that it's not going to be a different length here and a different length here. They're all the same length because the electrons can move around, and because of that, it's going to be shorter than a single bond but longer than a regular double bond. So it's a weird thing when the electrons can move around like that, when they can easily be here or here. They're moving around, and because of that, the bond length is actually going to be a little bit shorter than a single bond and a little bit longer than a regular double bond. So what that means is that it's in between the single bond length and the double bond length. Well, what I have in here is just double bonds. So my length would be the shortest here. Then in the middle, I'll have carbon dioxide because that's just the length of a double bond. And then here in carbonate, I'll have the longest bond because it's in between a double bond and a single bond. All right,